This is a non-trivial uniform circular motion problem, so it gets truly two-dimensional, and there are some tricks in it. But I still have this object traveling at a constant speed on a circular path. I've given numbers for all the relevant quantities here. The string is sagging at an angle of 50 degrees. The string is 1.5 meters long. And the mass is 0.5 kilograms, but I want to leave things symbolic until the very end this time. And so just to get an idea of what to do, I'm just going to start drawing all the force vectors in here. Gravity's pulling down. There's a string tied to this thing, so I'm just trying to look for every push or pull that I can possibly identify. And it's a short list on this problem. So I'm all out of pushes and pulls. It's just weight and the tension. This tension vector is begging to be broken down into components. And then maybe we'll figure out what the different components do. So here they are, and I should point out that the angle down here is the same as the angle up here. So that's our same theta of 50 degrees. And then I could just do a little bit of trig and write down that this is t cosine theta and this is t sine theta. Okay, so this object moving on a horizontal circular path, it must always be accelerating directly toward the center of curvature. So that's just a geometric fact about things that move in circles with a constant rate. So in other words, at this moment in time on the left, the acceleration is pointing this way. And I'm going to call that the positive direction for my analysis because that keeps things as simple as possible. And if I start grinding through the numbers here, I can do the horizontal analysis, the x analysis. I could say, well, what's providing the force to cause this center pointing acceleration? Sometimes you could call that the centripetal force here, but it's always a real push or a pull. So I have a net force of t cosine theta pointing to the center of curvature. And that's going to give me my acceleration in the x direction. The acceleration in the x direction is mv squared over r. But I want to point something out here. You have to be really careful about that r. I made it a little r instead of a big R because my radius of curvature here is not 1.5 meters. So there's a little bit of room to look at it over here. It's less than 1.5 meters. 1.5 meters is this hypotenuse. All right, and this angle, I suppose I'll just label, I'll label this angle is theta. So I have some work to do to figure out what the radius of curvature of this circle really is, and it's just trigonometry, but my angle is labeled a little bit weird. This r is the hypotenuse. This length right here is the radius of curvature. It's the same as this right here, and that's given by a cosine. So I have t cosine theta equals mv squared over r cosine theta. Okay. Then for the y analysis, I have that these two forces are balanced. This object just moves in a horizontal circular path forever. It never moves up or down, and that means the vertical forces must be balanced. So I get t sine theta equals mg. And there's a couple useful equations. All right, so now we should be able to eliminate one of the unknowns, which is t. You could go back and solve for it if it was asked for, but I'm just going to eliminate it here. And I'm just going to use a standard trick where I take the bottom equation and divide by the top equation. So I have on the left-hand side t sine theta over t cosine theta And on the right hand side, I have an mg divided by all this stuff, which is the same as multiplying by its reciprocal. So I have r cosine theta over mv squared. Turns out the mass doesn't matter. That's one benefit to keeping everything general. You can see things like that. And then the whole point of this manipulation was to cancel this unknown t. So I have solving for v, I'm going to multiply that over to the left hand side. I get v squared, and then on the right hand side I have a gr cosine theta in the numerator. And I have to divide by the sine function to get that off the left hand side and multiply by the cosine function. So then I can square root both sides, and I get square root gr cosine squared theta over sine theta. You can write that as a cotangent multiplied by a cosine, I suppose, if you wanted. And I plug everything in. 9.8, 1.5, cosine squared 50 degrees over the sine of 50 degrees. And I come out with 2.82 meters per second.